Welcome to Cohere Technologies and VMware's demonstration, doubling 5G capacity with VMware RIC and Cohere MU-MIMO Scheduler. In this demo, we will show how to unlock the true capacity of your cell sites with Cohere Spectrum Multiplier xApp enabled by VMware's RIC. As the telecommunications industry is undergoing a big shift towards Open RAN, service providers are considering how to best realize the true potential of their new deployments to future-proof and monetize their investments. VMware and Cohere Technologies are committed to enabling and supporting this transformation to Open RAN with proven solutions, relevant domain expertise, and key ecosystem partnerships to help their customers benefit from the RAN evolution. The VMware RIC platform provides the necessary abstraction to move business and operational intelligence away from the underlying data plane and into the control of the service providers and their application partners. The design of VMware Near Real-Time RIC and VMware Non-Real-Time RIC removes the complexities of integrating with the underlying data plane, offering xApp and RApp partners a platform that can help them deploy any app on any RAN and any cloud. Powered by the VMware RIC platform and SDK, this demo will show how Cohere's Spectrum Multiplier software enables MU-MIMO and Massive MIMO for both Frequency Division Duplex FDD and Time Division Duplex TDD networks in any band, under any mobility conditions, with any radio and any handset, while operating in the cloud. Given that the channel representation is based on physical geometrical aspects of the channel that change very slowly, the channel estimate is accurate and predictable across time and frequency. Accurate knowledge of the channel enables the formation of orthogonal beams to support multi-user MIMO in TDD or FDD. Orthogonal beams allow spectral reuse so that with the 4T4R dual polarized antenna, cell throughput is nearly double. With higher order antenna arrays, additional beams are supported for massive MU-MIMO. Orthogonal beam forming enables efficient spectrum sharing between LTE and 5G. Traffic is input to the 5G core using the traffic measurement tool iPerf and is transmitted through the central unit or CU and the DU user plane. The DU and radio unit are synchronized through a GPS-disciplined PTP grandmaster. The DU communicates with the RU through the ORAN fronthaul interface. The RAN server is configured for 5GNR standalone mode with a 20 MHz bandwidth, 256 QAM MCS22 and band N78. The channel emulator provides the 4x4 mobility channel between the 4T4R radio and the 2T2R CPEs. The CPEs or consumer premises equipment are a special type of user equipment or UE that are typically used to provide fixed access to the mobile network from a home or office. The CPEs are used in this configuration so that their external antenna ports can be connected directly to the channel emulator through cables. The plot shows a set of black dots that represent the positions of a group of 58 UEs whose distributions are from field measurements taken over several seconds of an actual LTE deployment. The plot shows a sector where the radial axis dimensions are in meters, showing UEs that range from about 200 to 1400 meters. The antenna is located at the position represented by the square at the bottom of the plot, and its bore side direction is up toward the 0° label at the top. A mobility profile was introduced where you will see that some UEs are stationary and others are randomly moving within the sector. As the simulation proceeds, it highlights the scheduling function where pairs of UEs are selected to be scheduled and pre-coded together. Pairs of UEs are highlighted with large blue circles. Along with each pairing, orthogonal beams are shown with the blue trace showing the beam to the first UE and the red trace showing the beam to the second. Note that the beams are not only adjusted for each pairing but also adjusted to track the relative mobilities of the UEs. The simulation ends by showing a specific pairing and the mobility characteristics represented by the emulated channel, which involve UEs moving at 60 to 100 km per hour. The channel emulator plays the specific mobility profile in a loop while we demonstrate the dynamic precoding and MU-MIMO capabilities implemented by Cohere software. The blue trace shows a beam directed toward the first UE, while the null is directed towards the second. The red trace shows it being directed towards the second UE, while the null is directed towards the first. The isolation between the UEs enables the scheduler to allocate the same physical layer resources to them, thereby doubling the capacity. The window on the right displays measurements from Cohere software. The thick black trace is the most recently computed beam for the first UE. The thick red trace is the most recently computed beam for the second UE and includes throughput and a representation of the beams derived from the computed precoder coefficients. For the first scenario, we've enabled traffic to a single UE so that it receives two layers in SU-MIMO. The layer 2 traffic measured by the UE and as shown on the left is about 115 megabits per second. For the second scenario, we will enable traffic to both UEs so that they share the physical layer resources in SU-MIMO. Since the resources are shared, the layer 2 traffic to both UEs is now about 57 megabits per second and corresponds to an aggregate cell throughput of 114 megabits per second. For scenario 3, we'll switch the configuration to MU-MIMO and we'll temporarily interrupt the throughput during the transition. We will enable traffic to one of the UEs. We again see the expected layer 2 traffic of 115 megabits per second. Now we'll enable the traffic to the second UE so that the MU-MIMO scheduler reuses the resources between the two UEs and the coefficient computation continuously computes the precoder coefficients to maintain orthogonality between the beams. Now we see that both UEs receive the full throughput so that the cell throughput is double. The layer 2 traffic to each UE is 115 megabits per second for the combined total throughput of 243 megabits per second. Now that the scheduler is allocating resources such that they are reused in each beam, coefficients are being computed and the resulting beam patterns are being displayed. The display shows the beam energy MdB as a function of distance and angle relative to the antenna. The thick black trace is the most recently computed beam for the first UE. Note that its energy is being directed toward the channel of the first UE and then is directing a null towards the channel to the second. The thick red trace is the most recently computed beam for the second UE. It is directing energy towards the channel of the second UE and the null towards the first. The coefficient computation is continuously using the uplink channel estimate to compute the beams and is therefore able to maintain orthogonality between the beams even with the mobile UE. This is reflected in the fact that the spectrum is reused and double the cell capacity is maintained. The thin red and black traces show the past measurements over about a 20-second window. For the first scenario with full allocation of resources to a single UE, the UE measured 115 megabits per second, which is also the sector total throughput. For the second scenario, with shared allocation of resources to two UEs, each UE measures 57 megabits per second for a sector total throughput of 114 megabits per second. For the third scenario, with the full allocation of resources to two UEs using MU-MIMO, each UE measures 114 megabits per second for a sector total of 228 megabits per second. This shows that the spectral reuse enabled by Cohere software and MU-MIMO with mobile UEs has increased the sector capacity from 114 megabits per second to 228 megabits per second. We have demonstrated the capability of double cell throughput by enabling spectral reuse to two UEs moving in a sector with a 4T4R antenna. Cohere software-based MU-MIMO offers significant benefits with no changes to existing handsets, radios, and antennas. Cohere software works in all available spectrum, enables true 4G and 5G coexistence. In this demo, we have shown how Cohere's Spectrum Multiplier software unlocks the true capacity of an O-RAN cell site, and it is a perfect example of the successful pairing between creative ingenuity in an xApp and the enablement provided by VMware's RIC.